So we are working with sequences, trying to decide under what conditions they don't converge, and that we could just make an argument that no matter what limit we pick, it's always going to fail, because here's an epsilon that player A wins the epsilon x game then. For that epsilon, no matter how far out we go, we can't get within that particular limit, and that's going to be the case no matter what limit. So I mean, there's just lots of stuff to try to argue there about the epsilon. No x works no matter what the limit is that we want to try to work with. And so from the definition of limit, it's not an easy one to say, well, the limit doesn't exist. So we moved into the idea that the limit could be headed off to infinity. So we need to talk a little bit more about that. So a sequence, A sub n is what's called bounded if there exists a capital K such that the absolute value of A sub n is less than K, or less than or equal to K, for all n. So in a sense, rather than doing what we do with the limit of for an epsilon, can we go far enough out that all the terms are within epsilon? Is there a K that if you look between minus K and K, all the terms fall in there? Not just from some point on, but really forever, for all the terms. Is there some value of K where that works? And if there is, then the sequence is bounded. All the terms are smaller than that K in absolute value. So, for example, this one then is not. Because no matter what K we pick, hopefully we realize I can go far enough out that n squared is bigger than K. So again, as with the epsilon x game, part of it is who gets to make the choice first. In this one, K is selected first. And if K works for all n, then it's bounded. But if we pick a K and then can go far enough out in the sequence where it's not true that the terms are less than K, no matter what K we pick, well, then the sequence is unbounded. So this particular sequence is unbounded. But just being unbounded is not really enough to tell us the sequence heads off to infinity. The sequence A sub n equals minus 1 to the n times n is also unbounded. But it's not headed to infinity. There's not a general trend of getting bigger and bigger and bigger, and in fact, kind of highlights our need to focus a little bit more what exactly we would mean if the sequence is headed off to infinity. How exactly would we prove that? Because we really can't get within epsilon of infinity. That doesn't really work. So our definition of this has got to be somewhat different than our definition of the sequence converges to a specific limit, which we can get within epsilon of and talk about no more than epsilon above or epsilon below if we go far enough out. This one's a different challenge. So we need to talk a little bit about that exactly. But this sequence is unbounded, and yet I would claim this sequence does not converge, or the limit doesn't exist. Not just as a specific number, there's not an identifiable trend in what the terms are doing. For much the same reason we had with some other examples we looked at on Wednesday, part of the sequence is heading one place, one direction, direction, part of the sequence is heading a different direction. So we could identify two subsequences that are doing something predictable, it's just not the same thing. So we get the same idea that we had with, I think we called it the first subsequence theorem, that a sequence would be divergent if it has two subsequences converge to different limits. If two parts would go to something different, the whole thing can't go to one value. Similarly, we get, kind of on this idea, what would be called the second subsequence theorem, or the second subsequence rule. That says a sequence is divergent if it has a subsequence that converges, or we'll say tends to infinity or minus infinity. Which is what happens here. One subsequence is headed off to infinity. We'd actually find another subsequence that's headed off to negative infinity. But for divergence of the sequence, all we need is one. If one is headed off, if we can find a subsequence that's headed off to infinity, there's no way the sequence can be converging to anything. So we don't have to really struggle, or all the terms getting close to infinity, whatever that means. We do need to talk about how are we going to talk getting close to infinity, as long as we convince ourselves that there's a subsequence that's headed off to infinity, the original sequence has got to diverge. So let's actually talk about this some more. What do we mean when we say the limit of a sub n being infinite? What do we mean by that? And we get if for each positive k, positive number k, there is a number capital X such that n greater than capital X implies a sub n is greater than k. So this looks a little bit like our epsilon x game. Somebody plays an epsilon, in a finite limit, somebody plays an epsilon that says how close you've got to be to the limit. Somebody else figures out, okay, it says, okay, from here on, or at x, from here on, all the terms are close enough to our limit. That's what we've been working with. Here, instead of epsilon, because there's really no sense we could get with an epsilon of infinity, player A plays a capital K, and player B comes along and finds a capital X, so that past X, all the terms are bigger than K. In a sense, if we can always do that, if player B always has a winning strategy, then in fact these terms do have to be going off to infinity. Because player A could say, well, use a bigger K. Well, there's a point somewhere farther out that we could go and all the terms are bigger than that particular K. Play a larger K, well, let's go farther out. There are places where we're bigger than that particular K. If we can always win that game by coming up with an x that goes along with the k, then the terms are headed off to infinity. And in fact, that's somewhat similar, or almost the opposite of what we've got here. A sequence is bounded if there exists a k, so that all the terms are less than or equal to k. Well, if we can't get a k ever, then we're at least going to have some terms that are bigger than any k we ever picked. In which case, if the sequence isn't bounded, there would have to be a subsequence that's headed off to infinity. If you couldn't bound it, say, by 100, there's at least one term bigger than 100. It's not bounded by 1,000, there's at least another term bigger than 1,000, or a term bigger than 1,000. Whatever size that term is, well, there's at least another term bigger than that, otherwise it'd be bounded by the size of that term. So we could argue very much that no matter what k we use, if there is no such k, no matter what k we try to use, there's always a term that's bigger than that, which would generate a subsequence then that would in fact be headed off to infinity. So we can work with that idea. But the advantage the subsequence rules have is we don't have to figure out what the whole sequence is doing. If we can figure out what part of the sequence is doing, and part of the sequence is behaving badly, then the whole sequence does. So the first subsequence rule, if we can get two parts that are headed to different values, the whole sequence can't be headed to any single value. The second subsequence rule, if we can get one part that's headed off to infinity, or minus infinity, there's no way the whole sequence could be headed anywhere in particular, since part of it's headed off to infinity. We don't care if all of it's headed off to infinity or not, just as long as some subsequence is headed off to infinity, that's enough to say the sequence is divergent. We don't care necessarily. I mean, we might come back to the question of, do all the terms head to infinity? Could we say a little bit more than it just diverges? Do all the terms head to infinity? But a lot of times just saying it's divergent is enough for us. Now, in a certain sense, we're actually almost more comfortable with this idea than headed to a specific limit. Because this idea ties very much into what we've looked at before on what's a null sequence. Get a couple reciprocal rules. The first one, if we've got a sequence that satisfies both eventually positive and the inverse sequence is null, then where do we think the sequence is going? If the terms are eventually positive and one over the terms go to 0, what do the terms have to be doing? Can we tell? I mean, if we think back to some of our sort of standard null sequences, even with those as we were kind of arguing they were null, what was sort of our argument? I mean, one of our standard null sequences was like 1 over n squared. How did we try to argue that 1 over n squared was null, really headed to 0?
Because n squared, when you pick
Yeah, the denominator was headed off to infinity. So I mean, we kind of used that reciprocal idea when we were thinking null sequences, that if the terms are going to 0, and the numerator is 1, and the whole term is going to 0, then the denominator's got to be going off to infinity. So that's what the first reciprocal rule says. And then vice versa, if the terms are going off to infinity, then 1 over the terms have to be null. And the reason these two parts look slightly different in terms of assumptions, here we don't have to assume anything about the sign. If we're marching off to infinity, it doesn't really matter if the sign is positive or negative. 1 over a big positive or a big negative is getting closer and closer to 0. But if it is marching off to infinity, it would be eventually positive. But it turns out the fact that it's positive really doesn't have much to do in showing that 1 over that is null. Whereas this one, we do have to know we're talking about positive terms to make a conclusion about a sub n, because 1 over a sub n could go to 0, and a sub n might not be headed anywhere. We could get big and then big negative, big and big negative, big and big negative. 1 over that would be heading to 0, but the terms themselves aren't headed anywhere in particular. So we do need here the additional hypothesis that the terms eventually are all positive, so we're not hopping back and forth. I mean, we could definitely conclude the absolute values are getting bigger if this sequence is null, but we wouldn't necessarily know what the denominator is doing until we know a little bit more about the sign of the denominator. So there are times as we work through different theorems, typically as we encounter theorems, I mean, if there's a hypothesis listed there, it's there for a reason. And if you pull that hypothesis, the theorem's no longer true. And we probably think of, and a lot of times I will illustrate kind of why that's the problem, or what makes a problem in that case. I guess this other hypothesis hopefully is fairly clear. If we've got a sequence that's eventually positive and we don't know anything about the inverse, why would we expect to know anything about the original sequence? We have to nail down something about the inverse before we can conclude something about the original sequence. So this one taken away, I think is a little bit more obvious. Why losing this? I mean, if all we know is the sequence is eventually positive, we really shouldn't expect to know much of anything about the sequence. We could be converging to 6, we could be verging to 25, we could be diverging. You know, we really have no way of knowing. We've got to know a little bit more about something to make a conclusion about the original sequence. But taking this away also poses a problem, just because 1 over a sub n is headed to 0 doesn't force the denominator to be going to infinity, because the denominator can be negative as well. So we do need to know a little bit more about our terms before we can conclude something about where exactly are the terms headed. Now, when our sequences are headed to infinity, suppose we have two sequences, both of them headed to infinity. What if we add them? Can we conclude what's happening when we add the two sequences? It also is going to go to infinity. What if I multiply them? That's also going to go to infinity. What if I subtract them? Yeah, we don't know. And hopefully we recognize we need to do a lot more work. It's not obvious in that case that this would be an indeterminate form. If we divide them, big number divided by a big number, that's also an indeterminate form. So there are a few ways we can combine sequences and know, oh, that's what's going to happen. There are some other ways that we might want to combine them that we really have to do a whole lot more work to figure out, well, what's going on there. Another theorem that could come in handy for us here is what's called the squeeze rule. If we've got a sequence that is headed to infinity and another sequence that we know is bigger than that sequence, can we conclude something about the sequence A sub n? Yes, I mean, that's kind of where the squeeze comes in. We've got a sequence B sub n that's trending off to infinity, and another sequence that's doing something, and it's always bigger than B sub n. A lot of times with the squeeze, we're putting the squeeze on between two functions, squeezing down to a value. Here, there's a sense we're kind of squeezing it off to infinity. If the small one's headed to infinity, well, that's where the big one's got to go too. There's no other thing it can do, and in fact, it has to go to infinity. It can't be jumping around, because if it were jumping around and never came down here, well, then that hypothesis isn't true. So with this hypothesis that we stay above B sub n, and B sub n's headed off to infinity, there's only one conclusion we can draw. Well, the original sequence has to be going to infinity as well. And so the squeeze rule, for me the squeeze rule is a fairly easy one to kind of illustrate, and we all understand why it should be true. It's a lot harder to put into practice, because when we have to put it into practice, we're given a sequence A sub n, and we've got to figure out, well, what do we think we can compare it to? And can we get a comparison sequence that does the two key things that we need to have happen here? We've got this sequence, we're not quite sure what it's doing. Can we find a smaller sequence that's headed off to infinity? Well, that pushes the original sequence off to infinity as well.
So would that be the same for the opposite then? So like if B of n is going to negative infinity, would you have A of n is less than B of n?
Yes, if we were going to negative infinity, we would need the unknown terms to be smaller. On this, say, so let's even look with this. If B sub n goes to infinity and A sub n is less than or equal to B sub n. So we've got B sub n and we've got some A sub n's that are smaller. Do we know anything about A sub n? Not a thing. Well, I guess we know it's all smaller than B sub n, but we don't have the inequality in the right direction to put the squeeze on to force A sub n to go anywhere. The fact that it's smaller than a sequence headed off to infinity really doesn't tell us much of anything. And so again, we've got kind of this scenario of what at first glance might look like a minor change in the hypothesis makes all the difference in the theorem. And that's definitely one of our goals of the class, is we're going to help you understand that as we read mathematics, the hypotheses we see, they are there for a reason. Somebody has studied it, and if we didn't need them, they wouldn't be there. So if they're there for a reason. It's good to sort of figure out, what that reason is. Because without them, the theorem's not true. I mean, if we didn't need the hypothesis, mathematicians would never stick it in. They don't just say, oh, let's throw this hypothesis in too. They look just for the most minimal set of hypotheses with that. And at some point, you'll be writing a paper kind of on that idea of how do changing your assumptions kind of change the outcome. I mean, this theorem, we change this one hypothesis, we now have nothing really to talk about. We don't know anything about what A sub n is doing. Or if B sub n were going to minus infinity, and it was a smaller one, well, we don't know anything to conclude about A sub n. We need both of these to make our conclusion about A sub n. One by itself is not enough. And I mean, in a study of religions, we could have quite a discussion. I don't want to try to get too theological here, but quite a discussion on sort of what are the key beliefs of Christianity. And if you pull one of those out, could you have a religion, but would it be Christianity still? I mean, Jesus is the Son of God. Jesus is the only way to salvation. That's what I believe Christianity says. We're all sinners. If you pull out any one of those, if Jesus isn't the only way to salvation, then you may have some sort of religion, but it's not a religion that other Christian denominations are going to say, oh yeah, that's a Christian religion. Because there are certain key tenets that all denominations and Christian religions have in common. And there certainly have been some times, I think, where different denominations start maybe having discussions. Are the places where we differ important enough that we say one's not Christian and the other is? I mean, I think most Christian religions agree baptism is important. There's certainly disagreement on how you do that. How do you perform it? When you perform it? Who decides it's time to perform the baptism? Those are some differences among denominations, but baptism is seen as an important thing to do. So you kind of have to decide in denominations, what are the key assumptions, and are there some things you could change that are okay? Another place I saw that illustrated when I was first started dating my wife. We went to a missions conference, and I wasn't Southern Baptist, and so we went to a missions conference, and one of the sessions I went to was, what does a missionary do in the desert when they need to baptize somebody? Water is an extremely precious commodity. Do you really want to put somebody in water and baptize them? And how does that go over in the culture to do that with that extremely valuable commodity? And yet, you believe baptism is important. You want them to understand the significance of baptism. So how do you do that? And this missionary shared that they had come up with the idea of a coffin. Dead to sins, raised to new life. Well, that picture does a whole lot more dead to sin, raised to new life, than necessarily going under the water. And so they needed to change a few things. They didn't want to change the meaning of the act of baptism and the significance of the symbolism there, but they wanted to do it in a way that they thought would be more culturally appropriate in that culture where water was such a valuable commodity. And so they had to think about how they were going to do that. I mean, Jesus talks about, I'm the bread of life. If you're in a culture where there's no bread, what does a Bible translator do with that kind of statement? You can't just make up a word if they don't have it, but you want to keep the meaning without, I mean, you've got to change the word some in terms of keeping the meaning. So you've got to be very careful of what things can I change, and that's okay, because it's preserving the meanings, and what things are such that, no, I really can't change that. That is too intricately tied with what the scripture is saying there, and the meaning, and so, is there any way I can get the culture to understand that? So there are a lot of kind of challenges with that, and the paper will kind of have your writing a little bit about that challenge of how you see modifying assumptions and what that does to conclusions, because we will have done that a number of times in math, but for you sort of in the faith realm as well. How does modifying assumptions end up changing conclusions? Okay, last time we also did some things with subsequences, and so I put together this diagram to try to help me a little bit. Sign of n. So we're going to sketch the sign of n. So here are like the first 2,000 terms of the sign of n. Do you think sign of n converges? I don't think it converges. How would we argue that it doesn't converge? Well, before this section, our choice would have been, well, you can't pick any limit. No matter what limit you pick, here's an epsilon that fails. But that's just a lot harder to go through. For no choice of L and no choice of epsilon, can you ever come up with a capital X? What is much easier is to think about our first subsequence rule. We could look here and I think convince ourselves there's some sort of subsequence that is converging to 1, or something close to 1. There's another subsequence, we could pick some things that we've got terms getting closer and closer and closer to 0. So we could get 2 subsequences that converge to different things. That's enough. 2 subsequences converge to different limits. The original sequence can't converge at all. Now, after I had this, I began to think, well, what happens if, say in the subsequence, we skipped every other one. So I picked like the first, third, fifth, 9th term of the sequence. So I'm going to highlight every other one. So there are a number of ones that aren't highlighted. I went with every other one and thought, well, that's doesn't change the picture a lot. Although even here, there's some interesting hexagonal patterns there that are kind of showing up. So I thought, okay, well, what if I skip every 2? Or I guess 3. So the first, the fourth. I'm not sure it shows up quite as well there. On my screen, I'm seeing kind of an up-down pattern of dots. And I'm not quite sure why this is vibrating a little bit.
Could be the air.
I guess. If we go to every 4, that's kind of interesting. I see these sort of stretched out lines. Every 5. What is that about? 1, 2, 3. Almost looks like 5 sine curves. Got 1 here, 1 there, 2, 3, 4. 5, but they all kind of look like a sine curve. Certainly not sort of what I was expecting. see. Come up here. Okay, from your angle it does look more. From my angle over here, I'm not seeing the sort of one sine curve up and down. It is a little bit more visible there. Certainly it's more visible on my screen than I'm seeing it from this angle. But I just thought it was interesting. And let's go back to this one where we kind of had the 5 sine curves. And so I wondered, well, I was doing, say, term 0, sine of 0, the 5th term, 10th term, 15th. What if I started, say, with the first term? So I do 1, 6, 11, or 2, 7, 12. I get the same type pattern regardless of which term I start with. So it's, looks like what?
It looks like it's moving.
Yeah, it does kind of, I mean, in terms of, in fact, I mean, computer animations are kind of that way. Here's a picture, here's another one in rapid succession, gives that. So yes, it does look like it's moving. But it's not really changing the pattern, which I found is an interesting thing, because I would have thought, you know, 1, 6, 11, etc. would have been different than the 0, 5, 10 pattern, but same type pattern.
Shifting it though? Is that not all you're doing, is shifting it? So why would it change the shape?
Well, if I was looking at all the terms, I suppose I would just be shifting it. But this is looking at terms 0, 5, 10, 15, 20, 25. I mean, the solid red dots are the terms I'm now focusing on. The black dots are the ones I threw away.
Yeah, but when you, I mean, you're still just shifting it on the thing, so it wouldn't change the way it looks.
Except, I mean,
I don't know. how to
well,
do you guys-
actually, I guess there is that sense, and I hadn't thought of that. That is illustrated by my, no, I don't think that's what it, because that's true. Sine n and sine, say, n minus 1, there is just a shift of 1, and that really is.
I mean, that's all you're asking it to show you, so that's all that it's going to show you. Like, that's all it's going to look like, obviously. Like, I don't know theoretically if there's any difference, but like, looks-wise, I think that's just what it looks like.
Yeah, that's true. So there is that shift. But there's 6. We go up to 7. I don't see a whole lot of pattern. 8, 9. 9, I kind of see some sine-looking curves. 10, I definitely see some more sine-looking curves. 11, interesting lines. 12, kind of one sine curve. So I just found it interesting. Some places I was discovering patterns where I really wasn't expecting patterns. I mean, from where we started, sine n looks to be all over the place. And it seems a little surprising to me that if I only look at every 13th term, I get something that looks like a sine graph. Yes, I'm picking some sine. I mean, I'm doing stuff with sines, but I'm doing sines of integers, and I'm picking every 13th one and getting an interesting pattern there. I don't know that we get any more with like 14, 15, 16, 17, 18. That one I found interesting. Just they almost look like lines. I suspect they're actually just really long sine curves that eventually it would curve back around as a sine curve and actually has some curve. But I don't know that. And also we've got these down here that stay, and then they start coming up. So I show this to illustrate what I also feel is kind of something that happens in math. You know, I drew this picture and I just thought, well, what if I do this? And I had a facility I could do. What if I do that? And see what happens and observe, and then try to think, well, why is that the case? Is there an explanation for that? oh, I was surprised, or maybe I shouldn't have been surprised, but we can kind of go back and forth and think, and that's really kind of how mathematics should work. I think a lot of times we're so focused on, we want to get these skills passed on to our students that we don't get sort of the joy and wonder of mathematics, that we tried something, oh, I wasn't expecting that, that's cool, why did that happen? And so how do we kind of come up with activities where we encourage students to just kind of explore and play and just make discoveries and then try to figure out, okay, why is that true? Would it always be true? How does that work? And that's kind of what we're doing with some of these. We've got this intuitive sense of, oh, we're headed off to infinity. How do we make that more firm? Or this, if both terms are headed off to infinity, how would we actually prove in general that, well, the sum's got to be headed off to infinity? If both parts are headed to infinity, it certainly makes sense that the sum has to be going. What would it look like to actually prove that? So, I think I've covered everything now in 2-4. So you should be in a position to look at 1, 2, 4A, 5A, and B in the section, and 4A through D at the end of the section, or at the end of the chapter. So some work with both subsequences and sequences headed off to infinity. And Monday we'll do another topic with sequences, trying to figure out where a sequence is headed when we really can't spot where we think it's headed. I mean, if we think it's headed to infinity, we have ways to show that. If we think it's headed to 0, we now have ways to show that. If we think it's headed to 1, we have ways to show that. But it very much keys on, we have to have kind of an idea where we think it's headed before we can show it's headed there. And so Monday we're going to look at, are there cases where we can decide, oh, it's headed somewhere without knowing where exactly it's headed? And if we do that, how does that help us? So, I will see you on Monday.